a conference thing I have to go to. So
What conference is it?
the quality improvement
Hmm.
one. So
Gotcha.
had the perfect break right in between it. So here, I'm gonna send you a couple papers I'm looking at the moment, so that way you can follow along if you want.
Okay, sounds good. Yeah, I finally decided how I'm gonna. This is unrelated. I've decided how I'm gonna contribute to the writing group.
Oh yeah.
Yeah, my boss wants us to consider writing a paper about the biotinidase method that we're working on, and it would be great to have uh, the expertise of you and Nicole as far as like what how I should go about it and stuff. I have a rough idea, so I've got some things that if the conversation dies down, I can pick up tomorrow. Otherwise, I'll just sit and listen.
That sounds good. Yeah, let me put that up there. Let me... So I just sent it to you.
Feature scaling?
Yeah, that should be it.
Yeah, accurate normalization of real-time quantitative. Whoa. Okay.
So what's been going on is that in newborn screening, there's a huge debate about how to normalize or scale the data so that way you can make comparisons across labs
Hmm.
and create larger data sets. And currently what they're doing is they're doing multiple of the means. Maybe I should put that in my slide set that I'm making right now.
Yeah, the multiple of the median as like a cutoff model.
Yeah, sorry, the median. Um, and there's some inherent problems with that methodology because it doesn't take into account the shape of your data set. And so if you have outliers on either end, if you normalize it or scale it based upon that, I need to quit using normalize because that's normalization something slightly different. That's just what everybody says in biology. Um, so when they scale it based on that, if you have any of those outliers, they're not going to go correctly.
Right. So who was I talking to about this? Because I actually did like an in-depth dive on multiple of the median. Let me look up who I was talking to this about. He's uh,
Was it Costas and his group?
um Burbage, Stanton Burbage,
Oh, I don't think I know that.
Burbage. Um, and we had a huge discussion about the multiples of the median because kind of the same argument that you're making, if you use the mean of your sample data and a distribution factor for it, it's going to your cutoff is going to shift whenever your population values shift, and so supposedly the multiples of the median is ideal because it doesn't get affected as drastically. Like if you're using the mean as a method of cutoff and normalizing it and everything, it it shifts periodically depending on reagent quality, the humidity in the air. There are a lot of quote unquote factors, but there was a big argument for multiple of the median being less affected by this kind of shifting.
Yeah,
So it's interesting.
in some regards that's true, but there's other, I guess, scaling methodologies out there that are more robust.
Hmm.
I guess because if you go into any other, so for some reason the multiple of the median is like alive and well in the biology world, but you go to any other data science area, they'd all raise an eyebrow and be like, "Wait, why are you guys using that? It's not a very robust methodology." And so I was going to talk about when Nicole gets on. Um, we can talk about some of the other methodologies that I found. And
Yeah, that'll be great.
I'm trying to remember. I used to do global mean normalizations based on housekeeper um, genes, but I'm trying to remember the exact formula for that, and I just cannot find it anywhere. Like everybody uses it, but no one ever gives the formula for it. So
Yeah,
it's driving me nuts. I'm like, yes, we that's it, but I need to know materials and methods. Oh, here we go. Yeah, we'll talk about them. We'll go through the math. I can share my screen really quick
okay.
so you can see where I'm looking at.
These are great articles, by the way.
Oh, thanks. No, we've had yeah, because when the CDC has been doing the comparing the multiple the median, what they like, because Nicole and I, and one of like before you came on to our journal club, we really broke down their paper pretty in depth. And I'm
Hmm.
trying to remember. And there was some. Is this it? Because we really just like went through it with a fine tooth comb and really went through it. Yeah, this is it. That's what we want. Um, because their idea is that they can do this multiple of the median and it normalizes it against this expected value.
Hmm.
And there's some of the values that kind of were jumping out at me. So like this value went from being super underrepresented, or this value went from being under the expected value to extremely high above there. And I'm curious as to why. And then this one did the same thing too. And
Yeah, and in fact, that second value that you pointed to was better from the better with the non-harmonized version.
yeah, and I'm really worried that if they were to do this type of approach, that, yeah, because we were looking at these two, and you can see here with after they harmonized, some of these got even worse.
Yeah,
Um,
but at least this data set looks like it's got like 100 points, whereas the previous one was only like 20. I assume all the pluses and circles are just different data sets.
um, man, it's been a couple weeks since I read this. I don't remember off the top. The each dot indicates a unique U.S. laboratory's PT concentration, and plus indicates a unique U.S. non-public health or international. So,
Okay.
but yeah, you can see with some of these, they just go like, and like if you're doing an overall, like if you're just doing a general type of analysis and you want to put through, it's not as big of a deal. But I feel like in healthcare, like with if some of these go way out, you're that's a big deal.
Yeah, because it's the difference between a false positive and a false negative, yeah, or the correct answer.
Yeah, and so then you'd have to have special conditions set up where like, all right, well, if it doesn't normalize to this, what like we'll have to try these other methods, and then you start creating these complicated decision tree algorithms. to
And
set
that's
it up.
gotta. Oh, sorry.
Oh, I was just saying there's got to be a better way.
Yeah, because at that point, when you're doing those multiple, what's the word? Not convolutions.
A convoluted.
Yeah, um, it becomes convoluted, and there's no way that there's no bias associated with saying, okay, well, if it gets normalized and it doesn't meet this criteria, then add this second filtering step. Like, you've got to be introducing significant bias at that point.
Yeah, so we've been going through and like the other thing that I was really hoping to see with this paper too was some sort of confusion matrix on
Hmm.
after they did the or the scaling of these to see if that affected, like, did that create more false positives or more false negatives? Did that um that's what I would really want to see too, and see what happens with that. But they didn't do that at all.
I feel like that's a critical point in your analysis, or the for the evaluation of your analysis is how many data points did it change as far as, you know, correct positive, correct negative, et cetera, et cetera.
Yeah, because if they could make an argument saying, well, everything was like we reduced all the false negatives and maybe we increased false positives, but you'd rather have increased false positives than
Hmm.
than negatives. And so, but I don't know. They don't have any of that data. And when we asked them about it, they said they didn't need it. And
What?
so they're like, why would we do that? We don't need it. And I was like, okay. It's like, it seems like a critical piece of information, but um,
Yeah, who are the authors for the paper?
um, it's it's from the CDC.
Oh, so they don't list the. There we go.
So yeah, I'm trying to. I can send you this one too.
Thank you.
I'll
Yeah,
put in the chat.
because I'm part of a group with the CDC for biotinidase, and it'd be interesting to see if they know anybody from this group.
Yeah, no, it's been interesting sitting in on it because I was like, I don't know. I'm not convinced that this is the better methodology to go through. And so
Well,
I've been going through, and later on this afternoon I'm meeting with the CDC, and so I'm kind of putting together a list of nor a scaling that's commonly used.
hmm.
And so one of these is um, one of the most common ones that's used, especially for metabolomics and um, microarrays, and I want to say RT-PCR or PCR techniques. Um, why did it do that? I want that all in one line. Okay, so there we do because I remember like I wouldn't classify myself as an analytical chemist. I know enough to get myself in trouble.
I love that phrase. No, enough
Okay.
to be dangerous.
Yeah, like I I know enough to get myself into a position I can't get myself out, but I
Hmm.
wouldn't consider myself an expert. But one of the things that I've seen a lot that I'm surprised, well, I guess we can talk about a little bit before we go to the paper that talks about this global normalization method and kind of work out the math. Um, and so what I can put in the slide is that you have a set. The idea is that within an organism, there's certain metabolites or genes that are homostatic.
Hmm.
And so if you were to collect like 500 metabolites and 200 of them maybe not necessarily contribute to disease, but you know that if in each individual they have to be within these certain ranges
Hmm.
for there. And even if you have one or two that are off because you have 500 other ones, it's not going to mess with the mean very much. And so then you can go through and you can normalize based upon the mean. And maybe that's what I need to Google really quick is let's look at mean normalization formula because maybe I can it'll spark.
Yeah. Feature scaling is the first one that shows up.
I know. Well, that's the this whole that's why I keep saying like I depending on what audience you're talking to, like you talk to biologists and they're like, oh, normalization, but what you're actually referring to is scaling. These are feature scaling.
Hmm.
And so you're feature scaling it so that way, and normalization is its own. So like this is the common normalization is the min max.
Hmm.
And so yeah, no, this is good. We have these totally on here. So this works. I can just put these formulas on. Yeah, so that saves us from having to work through this paper. Because sometimes these math things get pretty ugly. Even though it's
Especially
like,
because
oh, go ahead.
especially because half the time the paper doesn't give you the equivalence for all of the factors that they put in the equation. You're just supposed to know half the time what JKE is and you know lambda x or whatever. They don't give you all the names.
Yeah, and this one kind of does. I guess while we're here, we can walk through it really quick. Because I guess it's a good skill to know how to read math equations, especially in papers. So like here, they're saying J and K. So those are the values within a matrix. And they're going through, or the positions on there. And normally it's given as I and J. Oh yeah, so they have IJ here. Maybe I'm missing something. Yeah, so each of these are the housekeeping genes, J or
Hmm.
K. And so this is the coordinate on the graph, so that's 1, n. So if you had an n equals 1, that's the first variable or the number of variables. So like if you're looking at 300 genes, then this would be 1 to 300.
Got it.
And so j is equal to 1, k is equal to n, whatever n is depending on the size of your data set. And they're saying that j cannot equal to k. So
Which makes sense.
yeah, you can't do a normalization on itself. And so then we go to here. They're doing log base 2 of a, what's small a? Let's see if I can find it. The gene expression levels. So this is the gene expression level of J and then of K. And they do that all the way out. Then they take the standard deviation of what they calculated for A, which then gives us our value for the normalization. So this is sum of all the standard deviation values of that data set divided by n minus 1 of the total number of data points that
Okay.
you're doing for. So I feel like we could redo that if you want, but I like I think we could just do this mean normalization, but do a global mean.
Hmm.
And so, and part of what we do with the global mean is, as I said, you don't do everything. Well, you can do everything, But generally, you set aside a certain, as I was saying, a certain amount of data points that you're like, I know these aren't supposed to change.
Hmm.
And so then you go through and you normalize it based off of those. And I'm surprised that they didn't do that. Um, that they went to the multiple of the median first, besides trying something like this first, or this z-score normalization as well too. Because this is just the value minus the mean divided by the standard deviation. And so that one would work as well too.
Okay. To get really basic, these all are contingent on the data being normally distributed, right?
Well, this one right here, um, the z-score normalization, it creates a Gaussian distribution.
Okay.
Um, and you with the mean normalization, this typically will give you a value between 0 and 1.
Hmm.
Or not the min max one will give you a value between 0 and 1. So you might get like zero point 0.1 or zero point 0.8 um, there. And a lot of times with most neural networks within machine learning, you're going to have to do something like this. But I think what they're going to have to do is one of the problems that's been we've been having with newborn screening is that they've only been collecting data on features, molecular features that are indicative of disease, which for the past 30 years has been fine. But once you start wanting to use, like, do these normalizations and or the scaling of the features so that way you can use them all in the same data set or do comparisons across labs, you have to have more than just the variables you're looking at. Um, the more data, even if you're not using it, the better, is generally how it works.
Hmm.
Sorry, I came in late.
Oh, no worries.
But
Hey, Nicole.
oh, no. So are you guys talking about the data harmonization project that
Yeah.
is going on? Okay. Sorry,
Yes.
I just wanted to make sure.
Yeah. So we went through this paper that we did. We went over one of those other weeks before Scott came on.
Uh-huh. Oh,
And
yeah, so the same one that they published, right?
yep. And
Okay.
I was just saying that it's weird that they didn't do a confusion matrix
Well,
of
yeah, I wondered that too, but it seems like they didn't even get to the point where they would, yeah, do any kind of comparison, right? Because they did was do the method, but didn't show if it was actually like what the impact was on the as far as like false positive, false negatives, anything like that. Which I mean, I am not a math person, but that was the one thing I was like, huh?
yep. Yeah, because we were just because it just seems like that's super important because with some of these values going way out and becoming outliers, in my opinion, like it's important to know to make sure you're not inadvertent, like getting it wrong once or twice has pretty big impacts in clinical health. So
Yeah.
as I said, it's not like a terrible idea if you're just doing it for like normal, like if you're scaling it for some sort of other analysis, like having a couple data points outside is fine. But where we're in clinical health, you have to have it accurate. So
Right.
yeah, so we were just going through each of these methods and just kind of talking about them. We just went through the math on this real on this their normalization measures for this RT-PCR paper. I think that's what it
Hmm.
is. Because they're measuring the expression levels of genes and how they normalize that. And one thing that I'm just kind of pushing for is I think we should newborn screening needs to change up the way it currently does its analysis. So that way they can make comparisons across labs. And one of the ways they can do that is within each organism, whether it be like bacterial or humans or other animals, is you have a certain set of like metabolites or gene expression that are homeostatic. So they're not adjusting up and down drastically too much. Like there's usually like a baseline level of expression throughout for each
Yeah.
individual. And if you can normalize, normally what happens is they do some sort of normalization on those, and so they won't take the average of the variables that you're looking at of the observed values, but what they'll do is they'll take those other values. So if you pick up like 500 of those other data points, then you can calculate the mean of those and then do a norm. I always had heard it called global mean normalization. Blah, I can't speak. Is how we always did it in the bacterial world, and it seems like that's pretty common, ubiquitous through some of these other quantitative methodologies, whether you're using like microarrays or you're doing some sort of shotgun type of approach of looking at all the metabolites or proteomics or things like that. And so I am going to vote that newborn screening probably, even though they're not indicative disease, I think newborn screening needs to start measuring some of those values for those. So,
Yeah.
Quick question on that, Bryce.
yeah,
So the normalization of these values, I'm just curious how necessary it would be to standardize the methods of collection. So for example, in the paper, they're talking about mass spec analysis, right?
yep,
So from my understanding, when you're looking at some of these biomarkers, uh, the value can change depending on the method. So an example would be like derivatized versus non-derivatized, simply because you're changing the ionization efficacy of some of the biomarkers. And so what would be considered a normal range in, I'm just going to use a state, Minnesota, might be different in Maryland because of the method used. Do you think that is something to consider? Because we're trying to make cohesion between multiple newborn screening data sets, right?
yeah, and that's something that you'd have to actually look at. I would want to say if everybody's looking at the same set of LCMS data, that like if they're looking at the same molecular features throughout there, and even though the expression levels might be different, I guess I'm a proponent of maybe if you normalize or if you scale it correctly, they might come out the same. If not, then you'd probably have to have different data sets of this one for this one for that, and that's how you can only compare apples to apples and oranges to oranges, not apples to oranges. But I have the feeling that if you were to do that, it might shake out and be
Okay.
okay.
Yeah,
So
so I'm interested in what you said there. Can you tune the scaling? It looked like a very rigid mathematical equation. Can you alter it and tune the model for scaling?
yeah, so I guess one thing that maybe I can show you guys. Um, so this is a pretty common problem with an image analysis because there's so this kind of goes back to what you're saying is that even though you have different methods with different values, they it's the kind of the same thing that happens with images sometimes. So sometimes most images that you're going to deal with have a scale between 0 and 255. Sometimes they can be higher, sometimes they can be lower for those. And so sometimes I think it's like 0 to 60 and then 0 to, I can't even remember. There's so many of them. But you can convert those over. And so up to a 0 to 255 range. And that's, I guess, kind of my approach is like art is like if we can do that for images, even though they have different values and everything else, like we should in theory be able to do it on mass spec data, because in the end it's just you turn the image into a vector, and that can be go through the same process as everything else. So
Okay, that does make a lot more sense then.
yeah. Yeah, so I guess I'm just taking my image analysis knowledge and moving it over. But yeah, I was hoping they'd have an image of them doing like of a matrix of that. I guess they don't. But yeah, so the other part of what I was hoping to do today is let's pull out, now that we kind of talked about the problem and what's going on, I was kind of hoping to create some toy data sets and practice some of these scaling problems and on those data sets and kind of seeing how things shake out on the toy data sets that we're going to be running into. So, and we can just get the notebook started and stuff, and then maybe next week we can um, actually finish it up. So we'll just activate our environment on our Anaconda prompt that we made a couple weeks ago for Journal Club. Open up a new notebook. Let's call this scaling. Whoops, I was trying to open what we call that. I can't remember the flag for that. Maybe dash in. Yeah, so let's should we a new directory just in the command line. So I think we'll only need these three to do that. So we're going to open up NumPy, Pandas, and Matplotlib. So I'm going to throw you guys over there. Okay. So are you guys all caught up to where I'm at? Okay. So the first thing we're going to do is we're going to just create an empty data frame. Oh, I better make sure I don't screw this me grab a. Problem is I haven't actually had to like code anything in forever, and so oh, just empty. Okay. Ta-da! That should have been it. Is it just df.empty? That doesn't seem right. Oh, that's just to check if it's empty. We need to make an empty.
Is it just PD data frame and then just with empty parentheses?
Probably. So you're just saying like this?
Yeah, with a capital D and a capital F.
Oh, thank you, Nicole. So.
Oh, I have to look it up because you know me, I don't know Python.
No, it's okay. I haven't actually had to make like an empty data frame in forever. So the next thing we want to do is so we're gonna look at an empty data. And so there's a different ways we can do that. There's an easy. Let me look at it really quick. So there's a way we could do it where we can do it all by hand, doing each one, but there's a super simple function to do that. mp.round. No. Yeah, so this is it. So let's copy that up. I'm gonna throw that over there really quick. Okay, so I'm going to make an empty variable really quick of 500. So we'll just say 500 different metabolites that we're going to do. Let's do 300 and then maybe let's do 450, 50. So 50 is the number of features that we're investigating. 450 is all of our housekeeping homeostatic variables that were not really indicative of disease. And so let's make an empty, just make an empty list. That might be the easiest. Okay. So we're going to say for I in X. So we're going to do a for loop. Let's do x1 dot append. And let's add in mp dot. Well, I guess this will give us. Never mind. I'm doing it the long way, and I don't have to. So let's do homeostatic. Do mp dot round. Mp dot random. So we're using the random class. We want this to be a normal distribution. Let's have it the mean be 45, I guess, for this one, and let's have a standard deviation of 8. And then we want 450 samples. And then let's do, let's say the disorder one may or may not be around, we're just doing toy data, so never mind. B dot random dot normal. Let's have this be 45 again, and let's make the standard deviation bigger. So that way we have a bigger likelihood of some disorders popping up. Okay. So now we're going to stack these together. Is it homeostatic or homostatic? I think it's homeostatic, correct? Are you guys there? Yeah, I'm pretty sure.
Yeah, I think that's how it is.